You can go, Celso.
Hello, good evening, everyone. My name is Antonio Celso Jardim. I'm from SENS, and I would like to thank you all for your presence at the LAGO webinars, an event that we are bringing with great dedication to strengthen the bonds of our community. I would like to thank the sponsors, the FAPERJ Foundation, SENS, Nova Analytical, and Thermo Scientific, and our commission and technical team that is doing a great job. Please don't forget to follow our YouTube channel and our social media networks, and to join the association at the link available in the description of this video. We are trying to bring more activities and being always ready to bring news to our fellow geochemists. We want your participation, comment, interaction, and be part of our community. Please join now. Today, I have a pleasure to introduce Professor Fin Stuart, a good friend. And Fin is director and professor of isotope geoscience at SURB, Scottish University's Environmental Research Centre. Fin is an isotope geochemist with research interests that include the differentiation history of planet Earth and the generation of the atmosphere, tracing the source and the interaction history of modern and ancient fluids in the Earth crust, using cosmogenic isotopes to determine the controls of long-term landscape change, using low-temperature thermochronometers to constrain the tectonic history of the shallow crust. Fin runs his research at the Noble Gas Isotope Laboratory at SURB, and also frequently collaborating with scientists in the fields of petrology, geomorphology, mineralization, and tectonics. The presentation title today is The Use of Noble Gases as Tracers of Their Origin and History of Hydrocarbons Accumulation. So, Fin, please, welcome.
Thank you, Antonio. Thank you very much, and thank you very much for the invitation to give a presentation to you. I feel a little bit of a fraud here. This is an organization supporting organic geochemistry. This is a presentation not about chemistry, whether it is organic or inorganic. My presentation will be about the noble gases. They have no chemistry, but I've been asked to make this presentation, so thank you very much, and I hope you can take something from it. So hydrocarbon accumulations are a complex multi-phase systems. And what the noble gases have done for several decades now, we've used them to provide insight into the physical processes that control gas production, migration, and accumulation. And over the next 30 or 40 minutes, I'm going to give you the background to noble gas geochemistry, some basic chemistry of the noble gases, and I'm going to give you 3 examples of how we've used them, and then I'll say a little bit at the end about how we take the samples and a little about how we analyze them. Okay, well, every good presentation should start with geochemistry should start with a little look at the periodic table. Here is the periodic table, and you'll notice the column on the extreme right is the noble gases: helium, neon, argon, krypton, xenon, and of course radon. I'm not going to say anything much about radon, but helium to xenon are the elements that we conventionally study, and of course they are inert. They are the noble gases. They have a complete electron shell, a complete outer electron shell. So as a consequence, they are in normal surface conditions are not chemically reactive. However, they have proved over the last few decades to be fantastic, what we would call conservative physical tracers of processes that are extremely relevant to processes that go on in the crust, and in particular that might be of interest to organic geochemists related to the accumulation of hydrocarbon deposits. So they are gases, they are chemically unreactive, and they only respond to physical processes. So the physical processes that we will study will be related to diffusion and solubility rather than strictly chemical. Much of what we do is governed by partitioning between phases, in particular, so as it says here, solid, liquid, and gas phases, but in particular, in studies of hydrocarbons, we're largely studying equilibration between different liquid phases, between liquid and gas phases. These processes are strongly mass dependent, often governed by Henry's law. And the large mass range of this group of elements, we go from mass 3, helium-3, to mass 136, xenon, results in a huge variation of behavior, huge variation in, for instance, solubility, that really provides us with a very nice toolkit for studying a massive range of processes. And if that was all, it would be very satisfying, but it's not. There are two other very important aspects of the noble gases. The second one I would highlight, number 3 here, is that their stable nuclear structure is often a result of nuclear transformations. We would know, as geologists, we would know that as radioactive decay, these long-lived radioactive decays of potassium-40, for instance, to argon-40, the decay of uranium-238 and 235 and thorium-232 to lead produces an alpha particle, produces many alpha particles. In that case, produces 8, 7, and 6 alpha particles that very quickly acquire 2 electrons to become helium-4. And there are other more subtle nuclear reactions, such as the adsorption of oxygen-18 of neutrons to generate, that's the wrong way around. It should be the accumulation of alpha particles, emission of a neutron to generate neon-21. So we have these processes that go on, and they are very strongly time controlled. They provide a clock for many geological processes, not least those relevant to the formation of fluids. And the fourth line here, and this is extremely important, and in particular for many studies in South America, extremely relevant, is that there are several isotopes that are not generated at the Earth's surface. We could, or by radioactive decay, but are in themselves what we would call primordial. They were formed, they were generated when the Earth formed, and are still present in the deep Earth. For instance, the two that we would know most commonly would be helium-3 and neon-21, and they are most enriched in the Earth's mantle. They essentially don't exist, they're not produced in the crust of the Earth's atmosphere, so that the presence or not of helium-3 and neon-21 is very diagnostic of the influence of the Earth's mantle on melting of the Earth's mantle, production of magmas, and their intrusion into the crust, the release of volatiles and heat from those bodies can be traced unequivocally with the noble gases. So here is a very, very general schematic representation of all of the types of processes that, I'm trying to find the pointer, here we go, the types of processes and the origins of the noble gases in a very schematic representation of the Earth's crust. First thing to note down here would be the input of mantle volatiles, whether associated with intruded magmas that are degassing or deep faults. The injection of volatiles and heat can be picked up in crustal fluids. The generation of radiogenic isotopes, argon-40, helium-4, and this alpha N reaction that produces neon-21 also generates specific isotopes that we can use to trace and date, provide some sort of time constraint on geological processes. And then there's the what we would call the atmosphere-derived noble gases, neon 20 in the case of neon, argon 36, krypton 84, and xenon 130 or xenon 132. Many of us measure. They are provided largely get underground via water, meteoric water that's originated at the Earth's surface and is saturated and makes its way underground and then exchanges between different phases, between the different gas phases underground, and the patterns of those heavy gases provide us with some constraint on the physical processes that have gone on. We shouldn't forget also that sedimentary rocks, when they are deposited, also often accumulate the very heavy noble gases krypton and xenon, and they may be partitioned into they may be partitioned into oil from source rocks, and themselves impart a very nice indicator of the source that we can use and we can follow through migration and fluid interactions to inform the physical processes that have gone on in the generation of hydrocarbons. Okay, one more slide to demonstrate how the partitioning of these air-derived noble gases work in the Earth's surface. Here is a plot, a very typical plot that we would use, where we would normalize our air-derived gases, our air-derived isotopes, to 1. We typically normalize to argon 36. It's the most abundant and easiest to measure. So we will very often normalize our neon, krypton, and xenon to the isotope of argon and normalize that ratio to air-saturated water. Okay, so air-saturated water is a very diagnostic composition. It varies subtly depending on the temperature and the salinity of the water that's equilibrated with air. But that is our main way of getting these heavy noble gases underground, is in groundwaters. And equilibrating other gas or water or gas or liquid phases with air-saturated water, or exsolving the gases from air-saturated water in equilibrium with these other fluids, imparts a partitioning, imparts a difference in response to largely in response to solubility, which generates very, very diagnostic patterns. So you can see in this case, oil-water equilibration will tend to increase the abundance of the heavy noble gases relative to the light, whereas equilibration with gas will tend to have the opposite effect. This is not a complete system. This is essentially what happens when you extract the first few atoms. As you progressively degas the water to the oil phase or the gas phase, the composition approaches the original value, the original air-saturated water value. So we have to take care to understand that there's a time component to this as well. But the key thing probably that we would want to know about is that this can track the difference between open and closed system behavior. If you have an open system and you're constantly losing the gas or the oil from the system, you can strongly fractionate these elemental ratios and provide a very strong tracer of processes. Okay, so a little bit before I start talking about the examples that I have for you, I'll just give you a little bit of a background as to what these things are used for. It's fair to say that the study of the noble gases in oils is in its infancy, largely a result of the fact that the oils are extremely difficult to remove, and the presence of oil in our analytical apparatus, the presence of oil in our mass spectrometers. As a lab person, I can tell you that I really don't want oil anywhere near my mass spectrometer. So studies of oils are largely in are nascent, I would say. We largely dominantly use the noble gases for studies of natural gases, methane or CO2 rich natural gases are very common. and groundwaters. Now, the history of the use of noble gases and hydrocarbon systems goes back well, one could argue it goes back 100 years, but at least goes back 40, 50 years. And there is a huge literature on it. It may be relatively new to many in organic geochemistry, but it's undoubtedly very active, and I mean, certainly in the last 5 years, has become a very, very vibrant field. The types of studies that we would be doing with them relate to the residence time of fluids and the migration of hydrocarbons, the interaction of fluids. In particular, a major part of our studies is to use isotopes to figure out the origin of non-hydrocarbon gases, to understand how they might provide some knowledge of the thermal history of sedimentary basins, and when combined with geophysics, to understand how those gases accumulate relative to major structures. Increasingly, studies are being used in large hydrocarbon systems to understand reservoir connectivity and compartmentalization at reservoir scale. The radiogenic chronometers allow an understanding of the time of processes, so the time of gas charging, or the duration of how long gas bodies are accumulated. Increasingly now, as we move from an exploration to a unconventional gas world, we're finding that the noble gases will provide an absolutely unique fingerprint for unconventional gases that is relevant to environmental monitoring. And for the future, we will probably see more of that. I imagine that we will see the noble gases being used for carbon capture and storage, for hydrogen exploration, in particular for helium exploration as well. I'm now going to provide 3 case studies, one on unconventional gases from South America, another one from coal bed methane, understanding of how the noble gases provide constraints on the accumulation of coal bed methane, and the final one, if I have the time, on carbon capture and storage. So this is a study done by a former PhD student of mine, but in collaboration with Magali Pujol and many members of the exploration team in Total. This is a study of, as a case study, we'll look at the Vaca Muerta shale in the Neuquén Basin in Argentina. This, many of you will probably know this better than me, is one of the world's largest shale gas resources. It's been argued that it's the second largest on the planet, and exploration for and extraction of unconventional oil and gas has been going on for over a decade. The shales themselves are marine, Upper Jurassic, late Cretaceous in age. Maturation of the hydrocarbons likely occurred during the Upper Cretaceous, and hydrocarbon maturation has driven, or the hydrocarbons have been driven into the overlying Molotchinko Formation. The main issue for Total in this region was, or Total's affiliate in the region, was the fact that up to 10% of the gas that they would drill in these unconventional reservoirs in the shales was CO2, and it's impossible. At the time, it was very difficult to distinguish geophysically whether the gas that they were going to see was or where there was going to be any CO2, and it largely governed the viability of the fields. So we were brought in to do a study to try to understand the origin of the CO2 in the Vaca Muerta shale, and to provide some sort of constraint on how much CO2 could be present. Is there any relationship to the large structures? So we took a look at the molecular composition, the stable and noble gas isotope composition of gases from 2 fields that I'm not at liberty to tell you which fields they are in the southern part of the basin. So why is the CO2 important? Well, I don't need to go into too much detail about this, but these two plots demonstrate that the CO2, so these are the gases from the Vaca Muerta and the Mulichinco formation. We can see that in both cases they demonstrate that CO2 enter into the shales has displaced the heavy hydrocarbons and resulted in an isotope fractionation. So very early on, it was concluded that the CO2 injection into the shales occurred after the hydrocarbon maturation, and so was essentially a control on how much hydrocarbon was going to be present. This diagram is rather, or this image is rather complicated now, but what the geophysicists had spotted was that there were two generations of faults. That actually there was a series of deep-rooted reverse faults that terminated in the evaporite horizons, the purple evaporite horizon marked here, and then there was a second series of faults of strike slip faults that essentially were based in the evaporites, but cut the Vaca Muerta. And that what they had spotted was that the CO2 concentrations were highest where the two fault systems intersected. And so they could conclude from that that the CO2 originated below 2.4 kilometers, below the evaporites. But conventional geochemistry of that CO2 had not provided any constraint on its origin. So here's the plot now of the stable isotope composition of the carbon isotope composition of the CO2, plotted against what you will find is a remarkably useful tracer, which is the ratio of CO2 to helium, or the ratio of CO2 to helium-3, the primordial gas. So what we see, of course, is that the carbon isotope composition of the gases is really not particularly informative. It plots somewhere between the limestone values and heavier organic value that you would get derived from organic sediments, but they also overlap the mantle values, typical mantle values. So it's really not particularly diagnostic of the source. However, the low ratio of CO2 to helium-3 is a indicator, a very quick indicator that actually these gases are likely not crustal in origin, but likely originate in the mantle. And this is shown in a bit more detail here, where we have plots of the helium-3-4 ratio plotted against the CO2 concentration. Okay, so what I apologize that these two yellows have moved. The top panel shows that the helium-3-4 ratios are high. They're in the range between, essentially in the range between 3 and 4 times the ratio of air, which is much closer to the mantle value, which is around 6, which should be up here, than the crustal value, which is down here, which is essentially less than 0.1. This is the very, very diagnostic indication that the CO2 in the shale gas was magmatic in origin. Now, understanding or unraveling the mixing of the fluids is actually transpired was extremely important. The green bar here records a mixture between what would be the pure magmatic CO2, 100% CO2, and the pure hydrocarbon, which would essentially have very little CO2, and a helium-3-4 ratio that was indicative of the crust. So this is what we would expect to see given reasonable constraints on composition. This is the mixing relationship that we would expect to see. However, the data don't plot in this mixing relationship. So although they have a very high helium 3-4 ratio, they appear not to have any CO2. They appear to have lost most of their CO2, which may ultimately be indicative of post CO2 influx processes. Now, so the bottom diagram now is a diagram of CO2 against helium-3 plotted against that CO2 concentration, and we essentially see the same thing. We essentially see that the CO2 helium-3 ratios are significantly lower than the global and the local magmatic values. Okay, so they are almost an order of magnitude lower, implying again that the CO2 has been lost from the system somehow. Now, let's not go into too much detail here, but we've used we've modeled the evolution, as you would expect, by absorption of CO2 onto the shales to provide a limit on the amount of CO2 that should be in the shales. We've determined that the shales could contain up to 25% CO2 in some cases, which clearly poses a very significant risk for exploration. And Total were also interested to know when this magmatic CO2 came in, and we can do a little bit of fancy footwork. We can take and we can assume legitimately, we can assume the helium-3-4, the starting helium-3-4 ratio, and we can assume decay of uranium and thorium in the magma, or in the old magma, generates radiogenic helium-4 that lowers the ratio of 3-4 with time. And that is the lowering of that 3-4 ratio is plotted by this purple or this orange box here, and where it intersects the 3-4 ratio of the 3-4 ratio of the magmatic gas gives us some constraint on the time at which that magmatic body solidified. And it transpires, it's not super precise, that the intrusion it limits the intrusion time to between 12 and 34 million years. And there is only one realistic source of magmatism that could have generated that. And we think that would be when the Chile Trench collided with the South Chile Ridge around 14 million years ago, and there would be a kick, an onset of magmatism at the time. So we are fairly convinced that the magmatism has to be Cenozoic in age and probably is fairly late Cenozoic. So that CO2 has only been in that system for 10 to 15 million years. Okay, time is pressing. I am going to, that's the summary of this. This paper is published. If anybody's interested, I can pass it on. Okay. So a second case study now. I want to introduce the concept to you that in shallow hydrocarbon accumulations, the response to basin inversion, or the effect of rapid basin inversion on the retention of methane, can be traced using the noble gases. So this is an example that I'm going to take from China, from another PhD student of mine. Coal bed methane, for those of you that don't know, is the gas that accumulates in shallow coal seams, largely dissolved in the water in between the cleats and fractures, but also absorbed onto the surface, absorbed onto the coal macerals. Typically, the low porosity and the low permeability of coal seams means that often it has to be fracked to get it out, and but it has the rather positive advantage, at least in China, where this study was done, is that the extraction of the methane actually makes mining of the coal safer. So where are we? We're in the Liupanshui Basin in southern France, southern China, sorry. And this is it's a very old basin, but the coals in it are late Permian in age, and they have in the basin experienced several periods of burial and inversion and burial and inversion. And the reason why we've gone here is that we can sample from several blocks that have had different thermal histories, have had different burial and inversion histories, and different coal maturation levels, to try to understand what the effect, to unravel, in fact, the effect of coal maturation and basin inversion on the production of methane in the coals. So I'm going to concentrate on two basins, or two of these blocks, sorry. I'm going to concentrate on the QI block and the DA block. The QI block is the most extreme, is the most recently uplifted basin. It experienced burial, probably the coals experienced burial down to over 5 kilometers, 5.5 kilometers. And so consequently, it's probably been heated the most of all the 4 basins, but equally, it has seen the most vigorous Cenozoic exhumation, or the most vigorous Cenozoic inversion. Peak heating was probably in the Jurassic or early Cretaceous, but it experienced over 2 kilometers of inversion in the Cenozoic. In contrast, the DA block has been the one that's had the lowest maximum burial depth. It's been to no more than 3.5 kilometers, so maybe has got to more than 100 degrees centigrade. And most of the basin inversion occurred in the early Cretaceous. And in the Cenozoic, there's been very little. So we can compare these two, compare the methane in these two basins and look to see has there been any effect of basin inversion. So 4 basins. These are plots of vitrinate reflectance for the basin plot, the hydrogen isotope and the major gas on the C1 plus 2 composition of the gases, plotted against the carbon isotope composition. And what we see is actually very little isotopic difference. The gas is largely thermogenic in thermogenic in origin. It's rather simple in its nature. There's no strong evidence for microbial methane generation, and it appears that there's a systematic relationship between all the gas tracers and the coal maturation. So we think we should be looking to try to see is there any relationship between the noble gases and coal maturation level. First thing then to look at is the helium isotopes. All of the helium isotopes in these gases are radiogenic in origin. They're all crustal in origin. There's no need for mantle gases. There's no need, therefore, for mantle heat. So that implies that that all of the heating of this basin has been burial heating, and there's been no injection of mantle volatiles or non-injection of mantle heat required to stew the coal and make the methane. We can ignore the top figure. The top figure is largely irrelevant to us. It confirms this radiogenic, this crustal origin for the gases. And this diagram below is another isotope plot. This is a ratio of the ratio of argon 40-36, the argon isotope ratio, to the isotopic composition of neon, and we can see the data define 2 trends that essentially go through air. That the vast majority of the gases plot on a rather shallow slope, but the QI block gases on a much more vigorous slope, a much more vertical slope that can only be derived from the loss of neon, the loss of neon 21, this radiogenic neon component from the gases prior to mixing with air or air-saturated water. So this is the first indication that we see some perturbation of the noble gases as a consequence of likely as a consequence of basin inversion. So if we look a little bit harder then at the helium, the radiogenic helium, the radiogenic neon, and the radiogenic argon composition of the gases, well, we can tease out a bit more as to which gases have been lost and which gases have been retained. Okay, so this is a plot, and the top plot is a plot of just of helium-4 plotted against this radiogenic argon, the argon 40, and we can see that essentially the QI gases, those that have lost the neon, also appear to have lost the helium. In fact, there's very little helium in there, and so highly likely that a significant amount of helium from the gas phase has been lost in comparison to the others. Now, they plot along a line that's consistent with the generation of helium and argon in the rock itself, but we know that that is a minimum estimate. Frequently, in fact always, we expect helium to be in excess of this. So the fact that the data lie on this line are actually telling us that they themselves have also lost helium, but nowhere near as much as the QI basin. The same thing is reflected in neon 21. The neon 21 is showing an excess relative to argon produced in the rock, and that would be how the helium should be. But the QI block gases have also lost neon as well as helium. Let's come back to this to come back to the basin inversion histories. Just remind you that the QI basin suffered rapid pressure change, and it's the one that has lost the radiogenic helium and the radiogenic neon prior to equilibration with groundwater. So we think that this is showing, we're fairly certain, we've seen this in several places now, we think that we're losing by diffusive loss from the gas phase the noble gases that would be in the gas phase, but not the gases that would be strongly absorbed on the rock itself, argon, krypton, and xenon. And that's essentially what this diagram shows. This diagram shows, again, I probably shouldn't go into too much detail on this, but this shows that we have neon argon ratios now. So these atmospheric derived gases that are higher than air, extremely difficult to do without redissolving gases that had previously exsolved from solution. So we're probably seeing a reduction of pressure that is so strong, bubbles form and then re-equilibrate back with the fluids. So a rather complex system, even though it's just coal bed methane, rather complex system of generation of gas, loss due to diffusion, loss due to bubble production and generation of a gas phase, and then re-equilibration at shallow levels. I won't go into the details of the conclusions, other than to say we've developed a model that allows us to understand what this would affect, how this would affect the methane. And we consider that somewhere between 20 and 40% of the methane that would originally been present in the QI basin has been lost. How am I doing for time? Okay, so I've got 5 minutes. I will just have a little statement about carbon capture and storage and how we can use that to understand the fate of injected CO2. So the idea is that there are two types of tracers for carbon capture and storage. There are natural tracers that are already in the gases, and there are these anthropogenic tracers, these ones that are added to the gas on the injection. But nobody, at the time of this study a few years ago, this was the very first that utilized naturally occurring noble gases to be injected to trace processes. The study areas, Cranfield is a large enhanced oil recovery field that was abandoned many years ago, and in southern US, and it uses CO2 from a nearby natural CO2 field that was injected in, and as a tracer experiment over a period of a few years, we sampled the wells to understand where the CO2 had gone and what was happening to the CO2. So some objectives of the studies. Clearly, we wouldn't have done this if the stable isotopes had provided any constraint. They didn't. The stable isotopes of the gases from the injection and the production wells provided us with no constraint on what happened to the CO2 because they were on a rather horizontal part of the mixing relationship between CO2, between the injected CO2 and the naturally occurring gas that was So as we're finding in several places now, carbon isotopes are insensitive to mixing of injected CO2. Neon isotopes follow a very, very simple trend. This is 20 neon 22 plotted against 21 22. They provide us with the best way to distinguish the difference between the injected gas and the reservoir gas. We're also finding that neon isotopes are extremely useful for identifying these two. So when you translate that into our helium isotopes plotted against our CO2, the standard plot that you've seen before, what we find is the injected gas has a high helium-3,4 ratio. The natural gas with no CO2 in it has a very low helium-3,4 ratio. And here are the mixing curves between the gas injected in 2009 and the gas injected in 2012, where the data should plot. And the gas injected in 2009, we see largely falls on the mixing line. But we notice that the vast majority of the gases sampled in 2012 have suffered CO2 loss. They don't plot on the line, but they plot. So they plot to the left of this mixing line, consistent with the loss of CO2 from virtually every sample. Now, this trend is noted in other noble gases as well, but this was the first evidence that we were seeing CO2 loss. We had a range of techniques that we could use. We could use the helium-3,4 ratio in the previous plot. We could use the CO2 measured against helium-3, or we could use the argon-40 against helium-4. For the 4 samples which showed the most gas loss, we could use all 3 techniques to determine or to quantify the amount of loss. And there's a remarkable consistency between the 3 methods, the lower one being the most variable. And we could understand fairly well that in some places CO2 was being lost. However, we could make a decent estimation that only about 0.2% of the CO2 was being lost from the gas phase. Again, using a combination of CO2 helium-3, because CO2 is 30 times more soluble in water than helium, you really perturb the CO2 helium-3 ratio if you interact the gas with water. So you can plot CO2 helium-3 ratio. Frequently we plot it against isotope ratios of the noble gases, so we're not doing too much. We don't expect them to be changing too much. And we can see fairly nicely many of the samples plotting where along Rayleigh dissolution fractionation lines consistent with gas to water ratios that are really quite low. Okay. I think we can probably skip over that one. That's remarkably complicated. And here are the conclusions from that study. This was the first study to show that the injected CO2 we could quantitatively show that it dissolves in brines, but we could show that it only happens when the injected gas is low in comparison to the amount of reservoir fluid that was there. Otherwise, the CO2 is not trapped in brines. It actually seems to be just stored, what is called stratigraphic trapping, just in the porosity in the sediments. Okay, I will finish up with a very few words about how we take our samples. Probably the measurement details we can leave for another time, but I just want to let you know, if you're ever interested in doing this, you will probably be used to sampling in these lovely things in iso tubes and Tedlar bags. No, don't do it. Noble gases require all metal, and they require seals that are all metal as well, so no Teflon seals on them. So we use 2 apparatuses for sampling. We either use what I would call bespoke system of valves connected to known volume reservoirs. This is the kind of Rolls Royce. This is it has several advantages. They're expensive, and valve certification is time consuming, but if you have to ship them by air, this is the kind of thing that you might want to use. But it has advantages there. They're reusable, and they allow you to take 2 samples. So if one leaks, you've always got another one. We're Scottish. I'm Scottish. I like to save money. I don't like to spend too much money. So we have our alternative way of doing it, which is copper tube clamped between a pair of clamps. We can take, so this is sampling from a wellhead. You can sample as many, you can take as many samples using this technique as you want. It's relatively cheap, it's relatively flexible. However, if you've got to think in terms of sampling, it does require a bit more experience. This is Damakosh, he's an experienced sampler, so he knows what he's doing. It's not necessarily particularly easy to train anybody to do it that hasn't done it before. And these are not certified for air transport. So it's quite difficult in this day and age to get these insured to be traveling air if they are over 2 bars of pressure. Okay, that's me. I am complete. I'm finished. So thank you very much. I hope you enjoyed that. If you have anybody needs to contact me, this is my email address.
Thank you, Finn. Great presentation. So now waiting for questions to come. I have just a quick question. You have mentioned about environmental monitoring. So do you see already the European or American environmental agency demanding the use of noble gas monitoring?
Not demanded yet, and I think so. I can't speak to the US. I don't really know what's going on in the US, and Europe, of course, is stagnated fairly strongly now. There is moratoriums in most countries now in Western Europe against the extraction of unconventional gases. There's a little going on in the UK, and we would argue, as I think I've tried to demonstrate in this presentation, that many of the techniques that most of us have used for our lifetime, stable isotope, are not necessarily particularly diagnostic, not necessarily a particularly strong fingerprint in the way that the noble gases could be. I'm not saying that they always are, but they're another part of our armory to understand what is happening to gases coming to the surface.
Okay, thank you. We have a question from Shangru Kong from Apache Corporation. I might have missed the comments you have shown about the CO2 origin in Vaca Muerta basin. So he's asking you to say more, show the slide again, explain a little bit more about the origin of the CO2. And CO2 isotopes would be an important piece of evidence.
Yes. Okay. So, yeah, I'm sure I explained it very badly. So let me explain again. 2 sets of faults. Okay, deep. Let's just say deep and shallow faults. Where those faults intersect, it had been noted that the CO2 accumulations were highest. So it was taken from that to mean that the CO2 had to originate deep. Okay? The carbon isotope composition of that CO2, if you didn't have CO2 helium ratios, if you just had these carbon isotopes, it could easily be interpreted as a mixture of CO2 derived from the normal crustal sources. Okay? In this case, we're arguing limestone would have a value of about 0, and organic sediments would have a value of heavier than -20. So it's not necessary. So carbon isotopes could be interpreted as coming from the mantle if you wanted, but they could equally be interpreted as coming from a crustal source. So carbon isotopes are not indicative of the CO2 source. In reality, the helium isotope composition of the gases, sorry it's so small, but the helium 3-4 ratio crustal sources should be down here, should have a ratio of 0.01. Mantle sources, so deep magmatic source, would have a ratio higher than 6. Okay? This must be a dominantly magmatic derived CO2. This must be CO2 that's derived, exsolved from magmatic bodies. And our argument is that those magmas were in place sometime between 12 and 34 million years ago. So those magmas that exsolved the CO2 should be the second half of the Cenozoic. Okay?
Yeah, we're fine. We have another question from Alexandre Ferreira from Petrobras. Hi, Fin. Good to see you here. Could you comment to the audience a little bit more about how important it is the proper sampling procedures for noble gas analysis? So I can also add something about when you talk about stainless steel tubings and valves, so it's a concern about sampling, okay? So if you have any comments more about the stainless steel and the copper and the treatment you have to do in the surface or cleaning, how to clean it before sampling, things like this.
Okay, so yeah, so our main problem is that the noble gases tend to be very small. The key ones for us, the atoms are very small. Helium is extremely small. If there is not a good seal on the tube, helium will escape. And helium is usually in natural gases much higher than the gas concentration in the atmosphere. The atmosphere has a concentration of 5 ppm because most of the helium has escaped into space. Okay? So natural gases will always have a helium concentration higher than the atmosphere. So there is a gradient which it wants to go one way. It wants to go out. So if you leave any hole, if you leave any gas, any gap, so if these are not tightened up, if the seal on the valve is not absolutely perfect, on the metal, it will get out. And air will come in and the air will contaminate the gas that's in there. Now these guys, they don't have even what is down here. So these bags will equilibrate with the atmosphere really pretty quickly for noble gases, especially the light noble gases. These valves here, which will have Teflon seals, they may seal for a short period of time, but unlikely. And again here, push fittings and seals that are not very tight for atmosphere are very, very difficult to sample for noble gases. In this case, the valve closes with copper onto stainless steel, and it presses onto the copper and stainless steel. And we will only use this a few times, and we will replace them with new because they will be deformed. These would be cleaned of any hydrocarbon which is in there. You can polish the inside if you want. I'm not so bothered about that. More problematic is the retention of previously sampled hydrocarbon in there, which may linger in and contaminate mass spectrometers later on. But no, I think there is an expertise in generating these things. Now, these parts are all off the shelf. Okay, this is not hugely difficult to do, right? Getting the certification to allow it to travel by air is a little bit more problematic. But most of these cells are fairly good and they last for a long time. But you've got to just take some care to buy the right components and put them together properly. The other thing is, I could talk for hours about this. These seals don't always hold. You have to sometimes refresh them. And if the gasket that's in there has deformed a little, you may want to take it out and put a new gasket in and start again. So yes, it is definitely more expensive. It's definitely more problematic than what you would normally sample for, or let's say for organic geochemistry for stabilizers. We have to take a bit more care, but it's not difficult, I would say. I would say it's not difficult.
Yeah, Alexander is very concerned about the sampling. Everybody's here, Petrobras.
I mean, I think part of the problem is, once you've got this, part of the problem is actually having people trained on site to get samples. And that our biggest problem that we've had isn't with these, is that when these have been sent to a place and the person hasn't taken the care that is needed to take good samples, they usually will sample and they will get some air in. Maybe the care that you need with these is a little more than the care that you would need with these. And if the person is so used to doing these, it may be that if they don't use these properly, that is resulting in things. The valve is not closed properly, or the seal wasn't made perfectly when the gas was let in, so air came in. Yeah, things can happen. It's not just, so I'm saying, it's not just technology, it's also human beings.
Thank you. We have another question from Peter Hacksbacher. Congratulations, Finn. He's missing you. I use noble gas for provenance studies of CO2 related to mantle and crust contamination. Good question.
Yeah. Well, the example I gave from Vaca Muerta really is exactly it. That stable isotopes are very useful most of the time, but often it will not be particularly informative. It will not be particularly informative, especially when you can't go to the field and take the samples and do all of the field work associated. Helium isotopes and now neon isotopes are the diagnostic way. And I would urge anybody who wants to know the origin of their CO2, they really should be thinking to measure helium isotopes. It's not difficult, and in many ways it's not too expensive. It's becoming cheaper with time. I'm Scottish. I always think of how much it will cost.
Well, talking about cost and new stuff and technology, Alexandre Ferreira again brought a message about if you see significant improvements on instrumentation, like multi-collector machines, since our last conversation, or maybe our last meeting maybe 2 years ago. Did you see any changes? I think the instrumentation is be the same, and the performance is considerable, acceptable for all the recent research, correct?
Yeah, I mean, I would say, okay, so to get into detail, there are now 3 manufacturers, maybe only 2 really important manufacturers, but there are 3 manufacturers of instrumentation, probably 5 or 6 instruments that you could buy, given that there are those 3 companies. And all of them they're competitive now. So they are having to make advances in all sorts of departments. And we've just finished the 2-day workshop for noble gases. And all the companies are still introducing new angles. So new instruments are not being produced, but there's not a stagnation in the market. It's still quite a competitive market, and there's still advances being made in terms of electronics, in terms of sensitivity of instrumentation, of detector capability. There are always advances, and I think I'm very appreciative of the quality of instruments that Thermo make. But my advice to anybody is to look around and see what is available in the market for your own particular application.
So I complement asking you, do you see that the technology required for these instruments need to be improved in the future for more challenging samples? Let's say samples that will probably come from the space.
Well, yes. So there's several aspects to the improvement of the technology. So certainly for research purposes, yes, we would always like to be able to have more sensitivity so we can analyze smaller material. But in terms of what we want to do for gases, I would say probably as much of the improvement could be made in how we handle the gas, how we purify it, how we separate, how we let it into the mass spectrometer. Normally, if you have gas gas containers, gas sample devices like this, you've got more gas than you can handle. In fact, in my laboratory, when we're finished analyzing, we pump away probably 95% of the gas because we have so much. So actually, mass spec developments in terms of precision and sensitivity for gas analysis are probably not so important. Ease of operator, I think, would really help the widespread development of the technology to make it easy to use. That would be a really big advance, I would see. So it's not the preserve of, academic experienced users, so labs can start and get running very fast, but also faster throughput of samples. Right? I mean, it takes us 2 days to do one sample for all the noble gases and is remarkably person intensive. We need one person doing that all the time. It's very difficult to automate this. So there are things we could do, but and they're not all simply improving the mass spectrometer, I would say.
Okay, I think we don't have new questions coming so far. So we have no questions. So I would like to thank you very much for meeting you again here. It was a pleasure for us. And everybody sending messages here on the YouTube. I'm following here. So it was a very good presentation. So I'm proud to.
The pleasure was
all.
Yeah, I enjoyed that. It was good to do it, and it's a shame I'm not with you right now in Brazil. But there will come a time I will come.
Next year you're going to have this opportunity for sure, because today we have reached the last presentation of Alago webinars, and now our final message is that Alago is focused to bring us to the community the latest scientific trends in organic geochemistry to our community. Thank you, everybody. See you next year, next time.
Goodbye. See you next year. Bye-bye.